Hey Ramblers, this video covers chapter 4.4 and it covers two theorems, Theorem 24 and Theorem 25. And they're really the only theorems that I refer to by their number all year. They are actually referred to as the equidistance theorems, and they're really not two separate theorems. One is the converse of the other. The first thing to understand before getting into the theorems are what the term equidistant means. So we're going to spend a little bit of time just recognizing when to use this theorem. What does the picture have to look like? What is the relative position of the points involved in order to use this theorem? Then we will go through the proof and formally be introduced to the theorem. This is a very, very important and powerful theorem. It can be used to save you a lot of steps. The trick is recognizing when to do it. So please pay careful attention to the video, pause it when you need to, take notes, make a note card for this theorem, and I'll send you out another one tomorrow night to explain the converse. Okay, thanks for watching and good luck. Okay, the equidistance theorems are easy to use once you recognize when to use them. And the diagrams always have a couple of distinctive features. They call them the equidistance theorems because they're referring to 2 points that are equidistant from the endpoints of a given segment. So in this case, the points are P and Q, and they're equidistant from the endpoints of this red segment AB. Okay, let's take that a piece at a time. You can see I've measured out AP and BP are the same measure. So P is equidistant from the endpoints of AB. No matter how I move point P, it's always going to be as far from A as it is from B. So we say that it's equidistant from AB. Now Q is another point. That's as far from A as it is from B. So we say that since AQ is congruent to QB, point Q is equidistant from the endpoints of the red segment AB. Now, these two equidistant points, P and Q, they can be on opposite sides of the segment. They can be on the same side of the segment. They can even be one point beyond the segment. And the theorem that we're going to learn will still hold true. Okay, so what are we trying to prove? Well, we're trying to say that if we know 2 points are equidistant from the endpoints of a segment, so in other words, if PA and PB are congruent, and if AQ and BQ are congruent, then we can prove that the line connecting those two equidistant points will perpendicularly bisect the segment AB. All right, now I really want you to take a minute, pause the video, and try to do this proof yourself. It's a little bit of a detour proof, not too terribly difficult, but you're going to break it up into 2 parts. You're going to first prove through congruent triangles. You'll go through a detour, and then prove a triangle so that AM and MB are congruent. And then you'll show that angle AMQ and BMQ are congruent, so that they're supplementary and congruent and therefore right angles. Okay, take a minute and let's do that proof. I really think it'll help you to understand the theorem better and to know when to apply it. Okay, let's take a minute and let's go through the proof. We can see take care of our givens that AQ and BQ are congruent. And so there, by the reflexive property, PQ is congruent to PQ. So that means that triangle AQP on the left is congruent to triangle BQP on the right by side, side, side. This gives us this angle down here. AQP is congruent to angle BQP by CPCTC. So since QM is congruent to QM by the reflexive property, triangle AMQ is congruent to BMQ by side angle side, which means AM is congruent to BM, so therefore we know the segment's been bisected, and by CPCTC, angle AMQ is congruent to BMQ, And since the two angles are supplementary and congruent, they're right angles. Two segments that meet at right angles are perpendicular. So in step 10, we proved that the segments were, that PQ bisected AB, and in step 12, we proved that the segments were perpendicular. Therefore, QP is the perpendicular bisector of AB. Now, that was 12 steps, and the theorem is going to be this, that if we know 2 points are equidistant from the endpoints of a segment, then they determine the perpendicular bisector of the segment. So if 2 points, P and Q, are equidistant from the endpoints of a segment, the endpoints being AB in the segment AB, then they determine the perpendicular bisector. So the blue segment is the perpendicular bisector of the red segment. It doesn't matter whether or not the 2 points are on opposite sides, or if Q is on the segment, or if Q is on the same side. Either way, the proof would be very similar, and we could prove that PQ is the perpendicular bisector of AB. Okay, this theorem is a tough one, and it's one that students typically have trouble with. So I've included an example from number 1 of how to start recognizing the circumstances you need to use this theorem. Okay, so please watch the tutorial that I've included, and then we'll start working on problems tomorrow in class. Okay, thanks for watching. To use the equidistance theorems, we have to recognize when we have 2 points that are both equidistant from the endpoints of a segment. Let's take a look at number 1 in the exercises for section 4.4 as an example. Here they tell us that we have circle O. So by quickly drawing OA and OB, and since they're radii of the same circle, they'll be congruent. Then they tell us that M is the midpoint of AB. So M is as far from A as it is from B. Now that gives us 2 points, O and M, that are equidistant from the endpoints of a segment AB. So O and M we would call the equidistant points, and AB is the segment. So we're ready to use the theorem just by quickly jotting down the givens and some quick conclusions. Okay, so we write our givens, circle O, and then to draw OA and OB. That gives us our first pair of equidistant points. It's our first congruency showing that O is as far from A as it is from B. And then because M is a midpoint, AM and BM are congruent. So that's our second congruency showing that M is as far from A as it is from B. So now we have 2 points, O and M, that are equidistant from the endpoints of a segment, AB. So they determine the perpendicular bisector of the segment. Now, since we've proven a perpendicular bisector, that's more than we needed to simply show perpendicularity. So we can use this theorem to prove perpendicularity. Okay, there will be some other examples, but notice how, in this case, one point O was equidistant from A and B, and the other point was on the segment that was being perpendicularly bisected. That's different than the video, where I showed that the points were on opposite sides. Okay, hope this helps and good luck.